Hello.
Hello everyone. Good afternoon. We are still figuring out how to solve some technical issues. Are we good? Okay. Okay. So this talk in this afternoon will be remote. Unfortunately, Beidi was not able to make it in person, but she's going to give a very interesting talk on rethinking test time scaling laws. So it's a big pleasure to have Beidi Chen with us. Beidi is a professor at Carnegie Mellon University, and she's also a visiting researcher at Meta. Um, and today she's talking about test time scaling laws. Thank you.
Hello, everyone. Just to confirm, everybody can hear me, right?
Yep.
Okay, cool. Okay, let's get started. So today I'm gonna share a very special journey for the previous I think like 5 or 6 months of our entire lab trying to explore this new paradigm, which is like the test time scale and test time compute. You might heard of it or not, but you're probably using some of the techniques and strategies if you're doing any of these reasoning models like O1 and now every other like the chatbot or this kind of GPT-like software will have that functionality of enabling this thinking mode and thinking for super long and help you finish some task. So if you have this experience, this talk will be very useful for you to understand what is this thinking doing and what is the kind of the hardware support and the system deployment and the algorithm running behind it. Okay, cool. So let me motivate this talk with this Sequoia's, which is the top VC's 600 billion question. So I heard this question every year is double. Last time they asked is 200 billion questions, and they haven't asked it this year. So maybe now is a trillion question. So basically, the scaling law of the large models all point to the same thing that the key to improving AI model capabilities lies in more compute. So there's a lot of money put into this infrastructure. At that point, it was 300 billion, and they usually double it. Um, Basically, have invested in AI infrastructure, and the question is, can AI value surpass its cost sustainably, right? So basically, are we hitting another AI winter, or are we heading to Asia or whatever you call it to actually make profit and sustainable and keep going? So this motivates we studying the scaling law behind to answer this question is this massive compute, why we're putting this massive compute into this AI bat, right? So basically the first stage is from 2017 to 2022 on these model parameters. You probably heard that, oh, one company, another company is training a larger and larger and larger model, and it's like a competition, right? Who can stably train a large model seems to like they have more intelligence. And then the next phase goes to around 2022 to 2023 that they're no longer competing for model parameters because there's a well-known like scaling law study on if you double the compute, how much you put into your data, how much you put into your model size, and there's a underestimation how much you should put into your data. So from that point on, I think everybody who's training the model kind of start to focus on the quality and then the quantity of the data you can obtain. If you have the same compute, you put it compared to before into more of data. And in the next phase, which is around 2023, 2024, you probably heard that this company is training LM with 8K, 16K, 32K, and now 128K is the standard. And sometimes people announce I train like 1 million or 2 million like contact lens, right? There's a scaling on this part, and people start to believe that in order to enable any of the functionality of like supporting agentic task, coding, and all the rest, this long context is a basic functionality, and people believe like the longer you're closer to realize the AI to make it actually useful in many of the tasks we care, and especially in this agent and program optimization. And last year, um, there's this test time compute start to emerge. Basically, they're like theoretical works and their models announcement, and there's a lot of hype around um, the pre-training scaling is hitting some problems um, because we're running out of data. So remember, there's a scaling law, right? So because we're running out of data, even we have more compute, we're scaling the parameters suboptimal, and it's not improving to the speed that is optimal, right? So where are we heading? And there starts to be models out and research papers and also this series studies, basically depending on this long chain of thoughts. And this goes to the main topic we're studying today, which is all these thinking models and these models with massive test uptime compute and strategies. So basically, what we're trying to motivate in this slide is on the right of the screen, you can see this is cost per task in the x-axis, and y is the score or sum of the task in the ARC AGI evaluation data point from we got it from Twitter. Basically, it's saying that O1 or O3 is great, but it's even surpassing a STEM student's cost. So, and not also mentioning the speed, right? So it's not sustainable to do that. So the challenge is, although this scale continues, we'll find a new access scale. That's a great news. We rarely see something that you just put in more compute, you get more intelligence, right? It's very rare. So people are trying very hard to find the access that actually scales. But the challenge is very slow and it's not scalable, and you're paying more. Compute is not that cheap, right? So there are opportunities here is we're gradually shifting the focus from evaluation of perplexity, you probably heard, and token per second as a latency or throughput kind of a metric to soft rate. Did you solve this problem? I don't care how many you generate. I don't care how long you take. Did you solve this problem for me? And also task per second. Did you solve this task within the amount of time that I can tolerate, right? So why this is an opportunity? Because if you're hitting a PPL token per second, it's like very precise for each time of inference of your model. But the soft rate and task per second give you a wider design space as long as you can solve my task within some time. I don't care how you do it. So there's a lot of opportunity and relaxation we can do to exploit this shift to task time compute. But the key is you can see the scalability. So how much compute I put in, can I finish more tasks within some time? You can do it in parallel. It is okay, right? So some kind of a more background on this like test time compute strategies other than the ones of like really long chain of thoughts. You can use best of n. Basically, if you don't know how to do one math problem, you try to do that like 10 times or 100 times, right, in parallel. And then as long as one of the paths solve it, or you're taking your SAT test 3 times, you get the best score, which is fine, right? So best of n. And there are beam search and looking at search like some more complicated things with a combination of this serialization, like the long COT, and parallelization, like this best of n. So basically, there are like many different types of compute, but what this all points to is you're generating many, many tokens, no matter it's in a parallel or sequential or a combination way. So why is this generating so many tokens, making this kind of task time compute not actually as scalable as we would imagine? If you're looking at the three plots here, on the left-hand side is basically a trend of design for the modern hardware. The left one is GPU, the middle one is TPU, and the right one is the x-axis is the number of generated tokens and this flops per IO ratio, which is arithmetic intensity. So, for example, if you're computing a matrix multiplication, there are two things you need to do, right? One, load this matrix. Second, do the computation, right? So this loading is the memory IO, read and write. And it depends on your memory bandwidth of your hardware, right? And you do the matrix multiplication, which is floating points operation. So you do the computation, how much computation you need to do. So that is the flops. So you usually look at these two kind of descriptions whenever you see a new hardware come out. Basically, on the left side is saying that for GPU designs from V100, A100, L40 to H100 with more advanced one, this gap is larger. So your compute is growing faster than your memory bandwidth. And this is a nature and the cost and areas of design of your chip. And TPU is even worse. From V2 to like V6 is going from like 80 to 600, right? So your compute is becoming more and more cheaper, but your memory bandwidth, basically the time that you spend on your I/O, is not growing as fast as your compute. And why does this cause this problem for a lot of test time compute and a lot of generated tokens? The idea is it's becoming more and more memory bound. Once your hardware is getting better, you're bounded more by memory, and this long COT is actually exacerbating this problem. That's why if you're generating longer, doing the task better, you're becoming more and more memory bound, and this is not in line with what the hardware will grow. So that's why we call it this not scalable, right? So basically, in short, one shorthand is long channel file will result in increased memory access, which does not scale with the hardware. So what we kind of see in the high level of our recent work called kinetics of this rethinking test time scaling is previously what we introduced at the beginning of the talk. When people study this pre-training scaling, they usually saying that, okay, when I double the flops, so here, flops is the computation, which is fine. You can do that in pre-training. Why? Because pre-training is not memory bound, is super compute intensive. So basically, you can kind of using the flops to dominate all the time you spend with your hardware to do one task. But in the inference, the thing is you cannot do that because it's actually dominated by the memory access. But if you're using flops to measure if I double the flops, should I generate more tokens or make my model larger? This is not the right scaling you're studying. Your cost model is wrong. So we're saying we're contrasting these two cost models. One is you're just doing a theoretical computation on how many flops you're using, doing like solving this one task with generating these tokens with like a smaller model or generated less tokens with larger model. You would think that generating more tokens with smaller model always sounds, you feel like is cheaper. It is not because the memory access in resulted with a small model with a lot of tokens is way more than a larger model with less tokens. So that was the intuition. If you contrast these two scaling all on the left, you could be a 3x difference in your estimation. Basically, you thought you were deploying the most kind of cost saving solution. If I want to reach like 80% on my AMI task, I should deploy this small model with tons of generated tokens, call it a day. It is not true. You should deploy a large model with less generated tokens. So basically, that's what the kind of the rethinking part is you have to rethink this scaling law, not respect to flops, but this E-flops, which is the compute plus the memory times the arithmetic intensity. So this is equivalent kind of estimation of your cost model. Okay, so basically, in conclusion, because of the cost model is off in the previous work or previous scaling law, which are grounded in compute optimality, it overlooks critical memory access, so introduced by inference time strategies, which overestimate small models' effectiveness. So you should actually deploy a larger model. It's actually cheaper, which is very surprising. And let's see some interesting kind of scaling law analysis. So basically on the left side, this is isoflops, meaning that if you're seeing the same color, meaning that they're spanning the same like compute like equivalent flops. And the interesting thing is like if you see the x-axis is the model size, meaning that if you're moving across model size and you're generating the same number of tokens in thinking tokens, they're almost the same cost, right? Using our kinetic scaling analysis. And if you're seeing in the middle, in the previous scaling law, this is saying that if you're using the same model and you move vertically, no matter how many token you generate, you always choose a smaller one if you want cheaper, right? So you can see these two scaling laws are just different kind of these isoflops. And there's an interesting kind of architecture design trend is if you're observing for this OPT model to Llama to Queen series 2.5 to Queen 3, there's actually a trend on when you're doubling your model size, how much KV cache we're going to talk about. So that's exactly the thing that make this test time compute really memory bound and expensive. And you kind of see that the y-axis actually grows slowly and slowly with the newer series of models. So people notice this issue, and that's why they try really hard to kind of design some model architecture which are doing great, but at the same time not consuming too much things in this KV cache. And I believe for the other lectures, you're gonna hear about all this model architecture, including transformers, but other like linear models, sparse attention, and all the rest. And if from the test time compute perspective, they're differing in this KV cache memory. Um, yeah, so KV cache memory, I can introduce a little bit before we go into all these equations on analyze like why this is happening and why this scaling law shift is happening. So basically, what is KV cache? KV cache is after you're doing this like self attention, you're gonna have basically three projections, Q, K, V, right? And then the precisely why attention is effective is you have this Q attending to all your previous K and V's is kind of like KV is kind of your contextual memory, right? If you're regarding your parameters as your parametric memory, you're kind of like this KV on if you have a context, previous context of 100, all these 100 tokens are encoded, pre-computed, so that you don't need to compute again when you compute the new attention for your new generated tokens. Why? Because we're doing these autoregressive models. So your future generation won't affect the previous. That's why you can cache these memories or this context, basically, intermediate calculation. And that is kind of giving us the headache of this compute. So if you decompose the equivalent flops we're talking about here, and they basically have two components. One is the C comp, which is the computation. You spend something in this memory parameters computation in your linear layers and linear projections in your attention as well. So basically self-attention and both parameters-based computation, like MLP and WQKVO projections. And you also have your memory I/O kind of cost, which is also you need to load your parameters, right? That's you usually thought that was the whole bottleneck. And also the KV cache we just talked about. And it's growing linearly with your kind of the sequence length and generated length. So if you generate many, many, this will be many, many, right? So basically you're adding these two costs as your final cost. And remember that we care about this soft rate and task per second, meaning that if you actually want AI to be like the cost to be shared, you usually won't running one example on one model, right? That's very ineffective. You usually do the batch or you usually do things in parallel so that you amortize or share the cost. So usually we don't care about the model loading because that's usually can be shared. Let's say you have like a super large distributed setting, you have 100 batch size, and every single example is sharing this memory, this model loading cost. So it's shared. You don't need to worry about it. So what is actually growing with number of users who are using it is the other three, right? The more user use it, the cheaper you load it because everybody share it, right? Is economy. So basically, you can ignore this term, and the rest of the three compose as the actual main cost that when more users are using it, this cost will be linear growing. And if you plot it, as we see earlier, on the left hand side of the plot, this is saying that the more number of generated tokens you are, the longer your thinking tokens are, your attention time, like divided by the model cost, keep growing, meaning that your KV cache starts to dominate because your model is kind of growing slowly. Everything here growing slowly than this KV cache. Why? You see a quadratic term here, right? So basically, when you have a KV cache size is growing, and every time you generate one token, you have to scan it, right? Do the math. This is quadratic. So for the other ones, it's linear, right? So if we're doing like kind of theoretical analysis, but if you're actually benchmark it on the right, your KV cache access, which is in green color, just basically dominates for all types of models and sequence lengths. Even for 8K, it starts to dominate. It's not very long these days. Okay. And you might be thinking that in earlier slides we motivate that the power improvement does not solve this problem. It's actually making this problem worse, right? So if you're seeing this interesting plot on this like arithmetic intensity grows, which is like when your hardware grows better, your flops increases more, right? From V100, A100, L40, 800. What happens? So if you're looking at this line for the Queen 4B model or for this like 32B model, each of them you can look at it. So is growing like exponentially linearly faster with this like attention to model. So which means that your hardware just exacerbates this problem. If you're using 100, 800, majority of the time you spend is in attention. If you're using V100, maybe not that much more, right? So if you're using more and more hardware, advanced hardware, your attention becomes more and more the bottleneck. And you might think that we have all these like DeepSeek models. They seem to be very efficient. They're doing this like MLA like design, which reduce this KV cache size and all the rest. And they're doing this MOE, making the model parameter sparse. So does it reduce this problem? No. This is also does not help too much because if you're spending less compute on your model, meaning that equivalently you are spending more compute comparatively, relatively on your attention. So a mixture of experts is exacerbating this problem, and MLA does not solve this problem. It might reduce the memory I/O of attention. It doesn't reduce the compute. Okay, so attention still dominate the factor of test time compute. Now I guess the analysis is enough for you to understand why custom compute is actually not scalable on modern hardware, and then our duty is to how to scale it, right? So we identify two kind of possible paths of scale it. One is we can do some intrinsic parallel generation rather than solely the long COT. Maybe that will help. The second one is we can do some test time sparsitation. The first one is more of a modeling change. We'll no longer do purely autoregressive. That might help the problem. The second one is more of an architecture change. So what kind of architecture can maintain the quality of that stand compute strategies, but at the same time being faster and not unscalable, right? So let's talk about the parallelization first. So basically in one sentence, parallelization means scalability. And this is motivated and being implemented in a lot of well-known systems including like MapReduce, Spark, and all the rest. And in the end, I'll show you how we can achieve it by this analysis. So on the right-hand side, this plot means that remembering our attention cost becomes more and more dominating factors when our hardware becomes better, right? But if you're using the same number of tokens, let's say 32K, but doing it in parallel, like 8 parallel, same number of tokens, the scalability is much better. So parallelization will push the scalability. But the problem is our model cannot do parallel generation with the same task, right? You cannot solve A and A plus one at the same time. You have to solve A first. So let's see in the next work, multiverse. So your language model secretly decide how to parallel and merge generation. And I hope this is a strong motivation on why we're trying to design an intrinsic and native parallelization generation method going beyond autoregressive. So basically, you probably heard of not only the autoregressive models, there are diffusion text models, right? So diffusion model is massively parallel. Maybe that's the reason why Google is doing this text diffusion, because you see there are TPU arithmetic intensity is growing much higher and faster than the GPU design, which means that they design for more of this scalability and parallelization for their hardware, right? So basically, there are two kind of modeling, autoregressive and diffusion, but we're promoting for something in the middle, which is called multiverse, we call it. So we think that a lot of the computation should be serial and a lot of computation should be parallel. And let's not force it. Let's let the model to decide, do they want to parallel or do they want to do that sequentially? And autoregressive is purely sequential and diffusion is parallel, right? So basically why we're motivated to do this is because we kind of observe that the intrinsic parallelization exists in sequential chains already. So we did analysis on DeepSeek R1 reasoning traces, and we found that there are a couple of different parallelization structures that already natively kind of appeared in their reasoning traces. So this we summarize like two or three of them. The first one is there's a different path. You can solve one problem with Euclidean algorithm. You can solve the other one with prime factorization. Like you can just try a different path, right? A different attempt. That's one. The second one is sometimes you want to do one problem, but you have to try different use cases, A plus one, A plus two, A plus three. And sometimes you have to merge the result in the middle and then do it again, right? And sometimes you have to do some combination of you can compute the A and B and C in parallel and then merge them and then do something in serial, right? So there are different ways of solving tasks or trying different solutions and paths in parallel, sequential, or combination. The interesting thing is 90%, 99% of the examples of these reasoning traces, even they're generated sequentially, having this parallelizable branches already in there. And so in total in 99%, but majority of them is this collective branch, which is on this side, right? So there are some patterns in a reasoning train. So we think the model actually knows when do they need to parallel, when do they need to serial. And the question is, how do we force the model or encourage the model to do that natively? So first of all, we do a probing test on can model explicitly structure these parallelizable branches. And the classification kind of accuracy is almost half with random guess. They can't. So they can't decide when to parallel and when to, if not getting trained. So intrinsically, they can do that, but they can't, if you let them decide now, they can't, which means that we have to encourage them to do this. And what is the good way of enabling this intrinsic parallelism? We're machine learning people. We know what to do. Let it learn with the data and the task we gave them, right? So basically what we do is we're rewrite all these reasoning traces with a template and structure in a way that ask it to do a summary and identifying the nodes from the reasoning trace and identify different passes in parallel, if it's in parallel, and then merge them. So basically you have to structure your data, your training data from a sequential way to a very structured way. And insert the special tokens in the middle when you need them to parallel, when you need them to merge, when you need them to do any like summarization and conclusion, right? So basically, we form the data in a way that we can fit it to the model, and we need to, based on those special tokens, we can decide in parallel execution, your attention doesn't look into each other, right? You have to mask it. And when they're doing serial execution, they should be able to look into whatever is generated before. So you have to create this special structured attention mask to encourage them to do that. So you have to have the data, you have to have the attention mask, and then you start to train your model. And basically you encourage your model to, and the inference engine do the following. You have a summarization, what tasks you are going to do, and then you enter in this, generate this special token, you start the map stage. And you start to reason something in parallel, and then the model knows that, okay, I terminate this, I wait for the other branches to be ready, and then you merge together. So you have to this recursively map, reduce, and kind of keep going. And this is kind of the evaluation we see on AMI 2425 and Math 500 and GPT-QA. You can see this um, serial and kind of parallel, intrinsic parallel generation are on par, right? They're doing similarly, but this kind of serial generation, this parallel and or mixed generation kind of have this proof of concept on model is able to get trained to decide when to parallel and when to serial. And there are a lot of kind of possibilities. We can encourage more of this parallelism and integration into this language model. And here's a small demo on basically you have a question, you start to parallel your generation, and then you write some conclusions, and then you decide to parallel again, and you parallel, there's a parallel in parallel, and then you write a conclusion. So our model is able to make the model to, our training process of Multiverse is making model to intrinsically do this parallel and sequential generation in a model kind of deciding way. Okay, so let's get into the second part of the talk, which is we know that parallelization is pushing this scalability. What else? And it turns out that sparsity is also pushing this scalability. So sparsity is not new, right? It has a long history and even before machine learning, like statistics, neuroscience, and everywhere basically. But what is applicability in machine learning is it starts with this regularization to L1, right? Basically to prevent overfitting problems. And then from 2012 to now is using to reduce its training and inference cost. And for the future, we're anticipating sparsity as a way to increase models' capabilities. It's not a efficiency anymore because in test time scaling, the scalability equals stronger capability. So unlike pre-training, when the data kind of get, we're exhausting all the data, so the scaling law kind of plateaus, right? But the test time, once you put in more compute, your ability still grows. So whenever this situation where scaling happens, if you can scale better, then sparsity means that if your sparsity leads to scalability, means that it leads to stronger capabilities in test time scaling. Okay, so let's see how in this kinetics rethinking test time scaling, how we analyze this sparse scaling versus dense. So basically on the left, is kind of analysis on B200 NVIDIA machines on x-axis is the cost in the log, and y-axis is the accuracy of solving AMI task or live code bench. So there are a couple of plots in this talk. So basically you can see that the dense is the red one and the sparse is the blue series. And the different colors means that in the optimal point of let's say like 0.1 seconds, 1 seconds, or 10 seconds, we're choosing a different model. And the darker meaning that we're choosing like a smaller model. And the lighter color means the larger model. This is saying that when you have more compute budget, of course, you're going to spend more time on your larger models because they usually have more scaling factors there, right? In the high kind of accuracy regime. And yeah, on the right is basically another data sets. I think it's a live code bench. So it's basically coding and math. And you can see this clear gap on dense and sparse model scaling. So the conclusion is sparse attention is increasingly important with more computing invested for realizing the full potential of test time scaling. Because unlike training, the accuracy has yet to saturate as a function of computation. This continues to improve with increased generated tokens. So why the sparsity can mitigate attention bottleneck and scales better? So if you're looking at the left-hand side, there's a plot on the number of generated tokens and the attention. And we're seeing this bottleneck on the more generated token you have, attention becomes more of a bottleneck, right? And you see that with the sparse model, which is in the dashed line, it plateaus. Right? It plateaus on kind of around like 1,000. So 1,000 is kind of like our budget. So if exceeding 1,000, like 10,000 tokens, we're also the sparse attention will also only look at the previous 1,000. So that's why it's a constant. So you see, like by doing this sparse attention, you're able to push this like scaling down. This non-scalability is getting not resolved, not fully resolved, but getting better. And you can also see this like interesting scaling law study is when you put in more compute, which is like basically this on the right hand side of the plot, with more time and B200 seconds, you kind of see this sparse is scaling much better on the generate tokens, right? So with the same number of time, you can generate more tokens. And more tokens meaning scalability and capabilities, right? Within some time, you can answer something faster. And because giving you more time, you can think longer and you can answer better. So under the same time, you can answer better. And we're also studying some like scaling law of the sparse attention. So basically, now we have three variables. Whenever we study the scaling law, we have to have only two variables, right? So when you're double the compute, you should put into more of A or more of B. What is A and B here for sparse model? It's different than the dense. It's like once you fix the model size, you have a sparsity budget, right? Are you attending to only like subset of the tokens of 1,000 or 10,000 or 100,000 or 10, right? So what is your sparsity budget? And the other one is how many number of generated tokens you can do. These two are all both costly. Remember that quadratic term. So basically, this is saying that when you're doubling the compute, are you spending more time or compute budget on generating more, thinking longer, thinking more? Or are you putting into more like towards dense? Are you to reduce your sparsity? So this is saying that is totally towards you should just generate more tokens when you have time. Don't spend on your sparsity budget. So this means that, what does it say? It means that in the high accuracy regime, if you want to do some task that is very accurate and pushing the accuracy and boundary, you should spend your compute all in number of generated tokens rather than the sparse attention, the sparsity. So sparsity becomes more and more important in the high cost scenarios. So it's more scalable. And there's some like additional results on like AMI25, live code bench is all resulting, it's all consistently enhanced TTS across different scenarios. And also, what is interesting is now everybody is using mixture of expert model because it's efficient, right? So we're based on our analysis earlier, mixture of expert model just make the problem we described even worse. Attention will just dominate more because you reduce compute for your model. Then the bottleneck becomes the other ones, right? So in this MOE models of a Queen 332B, compared to like 32, 30B like active 3B, you can see that the scaling is very similar. So, and even better. So basically it is saying that in the ME models, whatever analysis we have is just even more towards we should just use sparse attention. And we run a Bayesian on different types of sparse attention. And then local or linear attention, I think, is kind of a one, conceptually one variant of them. But what is interesting here is this sparse attention is not something that is like you don't have it in your pre-trained model. And it's also not something that you cannot realize on your hardware. It is realizable, and you can directly do this with a pre-trained dense model. So you can just do a very simple block sparse model, block sparse attention. And if you look at the blue line, although it's not as ideal as the top K, like the kind of oracle sparse attention, it is very close and scales much better, right? Compared to dense. And unfortunately, the local, for example, just looking at the nearest sliding window, is not doing very well, meaning that for this test time scale, scaling to actually scale, it is also important to be accurate. So maybe you can reduce the cost, but if your cost, the way that you reduce the cost is not accurate using local or linear attention directly on the pre-trained model, it's not going to work. So maybe some distillation will help, but this block sparse attention is implementable and plug in and play on your pre-trained model. So we think this is not a theoretical analysis, but rather a realistic realization that we should use it. Why not? And on the right-hand side, this is our implementation with some like system backend. And you can see that you have the potential to reduce it, like the cost 20 times. If you're doing generating 20x more tokens, there are more problems you can solve, or there are harder problems you can push forward, right? So we really think this sparsity and this parallelization is the key to scale test time compute. And our lab has developed a lot of sparse attention method, and this block sparse is just like very simple variant and plug and play at the test time, but there are more fancier designs you can do. And let me run a summary on this lecture, what we have learned and what's next. So basically, we posed the challenge on this test time scaling is great and seems like it can help us solving all the math problems, coding problems, and maybe homeworks, right? But it's not very fast and it does not scale well. And there are kind of opportunities lies here from people care about solve rate and how many tasks you solve per second instead of the pure perplexity or number of tokens per second is like very fine-grained and constrained strategy metric. So you have a lot of design space. For example, sparse attention won't work very well. If it's perplexity or token per second, you'll lose accuracy a little bit. But because of this test I'm scaling, with the same amount of time, you always do better. So you never lose accuracy. You only scales better. So there's opportunities here. And the key is to push this scalability even further to kind of growing with our hardware development and our model advancement, right? Issue very fast. We give two examples how to do that. One is parallelization, and the other one is sparsity. So what's next is you think that this modeling and architecture design, many people might tell you that it's not that important anymore, and everybody's just using GPT or Cloud or Gemini, and no one knows how to design. I don't think that's true. Now the open source models are very strong, and there are a lot of test time strategies and even like agent strategies, which can make the even old models iterative number of times, and a lot of test time compute can solve the same kind of similar problems and try it at home. And but it is about the scalability. Can you actually do it within amount of time? So I think this like modeling and architecture design will still play a more and more important role as the model capability grows better. And they're also from the system side, since like at the end of the day, we have so many like uh, RL workload, um, training workload, and then inference workload, a lot of heterogeneous workload. And then as the motivating side at the beginning, basically at the end of the day, this AI investment is in the AI infrastructure, the majority of them. Then how do you leverage our resource better? It is the key. How to do scalability design. So maybe the system design should not be task centric, should be resource centric, right? That's how you not go into the AI winter. And also like their hardware co-design, very interesting things. And there are also like interesting applications. Once you scale this test compute, what you can do with agents, and can you train in a faster way with RL with like massive rollout and train a better model, right? There are many possibilities once you have a better scalability. So I think this is the end of the lecture. Happy to take questions if there are any.
So I guess we can take a couple of questions.
Hey, yeah, thanks for the talk. I'm not sure if you see me in the webcam. I'm like kind of at the back waving at you. Anyway, so question about yeah, I mean this whole thing, right? So I guess when you do the test time scaling, right? So there's this notion that there's some kind of these quote unquote reasoning traces, right?
Mhm.
Um, like how much of hallucinations are an issue for that? Because I would
Oh
imagine that if if you have like some small details hallucinated, then
yeah, quite a
basically the whole
lot
inference just
actually.
goes to garbage.
Yeah, when you look at
And
it.
what do you do about that?
Yeah. So basically the interesting thing is, I think that was recently found in this like Coin 2.5 model mass and something is like there are a lot of things that a model already can do. And if you're just doing RL not to the extent that you actually making it learn, it's kind of adapt to your prompt, right? It's just kind of make the knowledge that the model already know kind of out. And so that's like one of the problem. And when we look at these reasoning traces of DeepSeek R1, it's very similar. It's not reasoning in a way that you're anticipating it's reasoning. It's just like generating some random things, and sometimes like the reasoning trace will also be like is solving one problem, and then they're analyze a special case on a equals to 0, and then they call it optimal, and somehow the answer is correct. So there are actually a lot of guesses and some coincidence and some of the things like you can't even understand why the model can get it right, the final answer. Yeah, so basically, I don't think that's like there might be two reasons. One is can be hallucination, and the reason why is like model is doing some internal computation and reasoning not directly out like reflect on the generated tokens. The other one is the model is purely hallucination, has hallucinated, but it has some memory or it kind of knows some knowledge so that once you do the like long COT, they somehow can guess it in the end, even their reasoning process is incorrect. Yeah, so there could be like two kind of reasons, and we're looking forward to have future studies on what is actually the model is reasoning, and that they actually hallucinate things and just extract some knowledge they memorize and somehow like combine it out and guess the answer, or are they actually able to use all this long reason traces, this computation they're doing, even it's not explicitly mapped to the token they generated, but it is somehow doing some internal computation. So both sides are possible. So I'm more tailored to the second one, to be honest, because like I think that would be like too much of a coincidence. The model can solve a lot of tasks that I'm aiming for, and not only the aiming or the live code bench, right? So if you're using all these closed models and APIs, they're actually help you to solve some of the problems. And there are problems that I don't think they maybe they saw before if they memorize everything. That's probably generalization, but that's a larger problem to discuss. But I'm more leaning towards like model, at least for a large amount of fraction, it's actually able to solve some of the tasks that they do it correctly. But yeah, of course, there are a lot of hallucinations on the other ones.
Okay. Uh, Nice to meet you, Professor Chen. My name is Wang Su, and I know your work makes the modeling more effective and faster, better. But there is some user, such as the hacker. How do you think about the information security? The relationship between the information secret and your work? Yeah.
Yeah, so basically we have other projects actually. So if you heard of Sweet Bench, so basically is a benchmark to evaluate if your model with some retrieval agent to can help you to fix some bug on GitHub real issues. Is it environment, there's sandbox, there's tests, right? So we're actually working on attacking it, meaning that you let the AI or you let the model to help you fix your bug. They can have some malicious kind of issue there, which will drive the AI model putting some malicious code in your code base. So I think this is all on safety, safety in a way of like code security is going to be a massive problem once disabilities become stronger and stronger. It's very easy to attack those large models. And I think this research is going to be more and more important, not only in the capability, but people are going to use it to do malicious things. And then if we're automating a lot of tasks with AI, and they're going to be much easier to be scammed than people. So it's going to become a very important problem. And yeah, it is there. It's very vulnerable.
Okay, thank you. Thank you, Professor.
Thank you for your talk. I had a question that relates with the first one. So Anthropic released a paper, I think last week, called Inverse Scaling in Test Time Compute, in which they show that if you put too much test time compute in some tasks, it can actually lead to lower accuracies. And this makes sense intuitively because the more steps you take, you are compounding the probability of having an error at each of them, right? So do you think that, and I didn't see this before, when we were scaling training, right? The more we scaled, the better the models were. They didn't really get worse at tasks, right? So do you think that for test time computing, this is different? And for example, that for a particular task, there's some optimal amount of flops that we should use, or that this is not really what's happening?
Okay, yeah. So I will answer your question in twofold. That's a very good question. So we're thinking that if we're putting more computing in training, it's always getting better. It's actually not always true. So there are some analysis and evaluation and angle you might not kind of notice. For example, if you let the model memorize much more and better, it occupies all this capacity. It's also a blog published by Anthropic on this like superposition and compositionality. So basically, it's saying that the most efficient way of expressing this information, the number of bits, there, if you compress it a lot, it's very efficient, but it's not composable. So you basically memorize in a very efficient way, but maybe it does not generalize or it doesn't learn how to combine things or concepts better. So if you don't compress them, you let them just compose, it's not very efficient. You'll be super high dimensional sparse, and you also don't learn well. So usually what the model will do is somewhere in the middle. So there are some interoperability things. So there's a recent work in this memory mosaics follow-up, our work. There's kind of at a scale of maybe 7B model and more on the Llama. And you think that if you're training more tokens to be like inference optimal because you want to train a smaller model is stronger. It's actually not true. They memorize better, but they suffer on this in-context learning abilities. So it is, first of all, the first half of the question. So even you overtrain your model, sometimes bad things will happen as well. Maybe not the metric you're talking about, but there are other things, there are other abilities they're balancing. That's one. The second one is yes, I think in the task-time compute, if you're lacking in thinking more or something, it's not always better. This is true. I agree with this opinion. But sometimes if you're thinking about it, there are tasks you need to have enough explorations, and you need to have enough number of tokens to do that. So what Anthropic's kind of talking about, it depends on the regime and the task. So if the task is naturally and natively very hard, like all these Amy tasks compared to mass 500, they just need more tokens on average. So everything is about expectation in this task, right? So I think it depends on the situations. They are tasks, which I think you don't need those many tokens, and why. Like that's why model starts to have like the sync and non-syncing mode hybrid together. And model should be able to decide that, to be honest. I think that is actually the intelligent part. So the model have to decide that. And they are tasks which is deniable, like long coding task and long, if you're solving like Ferris theorem is like 88K tokens in the proof. You cannot avoid, right? So they are tasks which is information dense and uncompressible and very long. And there are tasks which is easy. So I think it depends on the situations, and it's all about expectation. This type of task is kind of difficult or requires more tokens or not. So I think this analysis and task time scaling is still meaningful in a lot of kind of tasks which is harder, serial, and with more difficulties. But like what we see in a multiverse, there are things you can do in parallel, and not everything you should do in sequential and hardest way. So I guess like task time scaling was really long COT is just handling the worst case.
Right, thank you.
So I think we have time for one more.
Hi, thank you so much for your presentation. I wanted to ask about the multiverse model and how it works exactly. So, because you said it was sort of a mix between autoregression and diffusion, like, could you just explain a bit more how that works? Because from my understanding, it seems like you sort of parallelize several LLMs from this like demo that you're showing now. Is that what you're doing? And like fine-tuning with a specific parallelized mode or something like, or yeah, I guess could you just give some more details on that?
Yeah, of course. So diffusion is kind of a different mode. It is usually generating one and start iterating. So there's not like dependencies on this like autoregressive way, right? But autoregressive is like one token after the other. So I was just trying to say that multiverse somewhere in between. It's not a mix, but more of a something in between. It's like sometimes it's sequential, sometimes it's parallel. And like what you said, so here, for example, in this case is these two are parallel, right? And this one and another one is parallel, and they're parallel in parallel. So basically, they are, if you're regarding your generated tokens as a chain for autoregressive, this is basically a tree or graph. So that's the difference. And you're using the same model, not different LLMs, just one model. Sometimes you can parallel generate three, sometimes you generate four, sometimes you generate one. And your generates like a tree or graph because you do merge as well. Yes.
So it's not like another agent or something. It's
Yeah, it's the same model outputting those tokens. Yeah, that's why we train the model end to end.
Okay, thank you. So we have one last question.
Hi, can you hear me? Thank you for the talk. What is your insight on the shotgun approach, which is a test time compute and generate multiple parallel answer at the same time? Should we do more deeper answer? Is it better, or wider answer, like more number of answer? The analogy is like letting the same student do 3 times the same exam 1 hour or 20 times 15 minutes.
Yeah.
Any insight?
Yeah. So I would answer this question from two perspectives. From the system perspective, if you're generating same number of tokens as we show earlier before the multiverse, I believe, parallel is always more scalable and better and faster, right? So that's from the system level. However, from the machine learning perspective, I think they are tasks like what we just said. You need some serialization. And my hunch is these two are orthogonal to each other in a way that the scaling, oh, you are gonna hit some diminished return on the long COT. And that point, that's where you start to do this best of n. And you kind of see like minimax start to have like 80 something K number generated tokens, and you start to see like it's hitting some diminishing return on generating more. And in serial, they start to forget things and they start to don't know how to reason, and they also like going in the loop. They start to not doing well with the long COT. But before the diminishing return happens, I think maybe that could push really like model to rethink, reflect, look at its arrows. There are like different abilities people trying to study in this long COT. It's very interesting. And this best of n is kind of like more of a probabilistic thing. It's like the probability you do one problem, solve one problem in 0.1. This best of n is just like increasing this with more trials. So I think from the system perspective, I would say like best of n is more efficient. But from the machine learning perspective, this long COT, how to do this reflection and then studying this behavior and why is hitting diminished return and does the arrow propagate with this autoaggressiveness is way more interesting. So I think there's no like one is better than the other, but what perspective you're looking at.
Okay, thank you. So let's thank Beidi again.
All
Okay,
right.
so
Thanks,
thank
everyone.
you and enjoy your evening.
Bye.